So if you look at this particulate level diagram, okay, what we see is 3 black circles, red, several white around. Here we've kind of seen this molecule already. This is water. So you see the red and the 2 whites. You mix the 2 together and you come over here. If you look closely, you have red and 2 whites, red and 2 whites over and over. Right? You have 3 blacks, red, several whites, 3 blacks, red, several whites. And so there's been no change at the particulate level. And when that happens, it's very different from what we saw with our chemical changes. This is just a physical change. And what's going on here is actually mixing. So we're making a solution. We're dissolving the substance in water. Okay. Now, this next picture also shows a physical change, but it looks much different from that one. That was pretty easy to see. Same, right? But this, we got a little different stuff going on, okay? So here you see the water, okay? And so here, this is an ionic substance, ionic solid. You can see the negative green, the positive yellow there. And then what happens when you mix these together is we get this dissociation of ions. But there has really been no change in what the ions are. They've just split apart. And so that's why this is still considered to be a physical change. Although, in just a minute, we are going to see that some of your physical properties are going to change here. So the dissolving of ionic substance is one of those changes that there's a little bit of debate about. Some ionic substances, when they dissolve in water, you have a release of energy. Some you have an absorption of energy. And those things are usually reserved for chemical changes, okay? But dissolving, we will say, is a physical change because you don't really change what the substance is, or there's no real change at the particulate level, except you do get just this split apart into its ions. Okay, so what we're going to do now is kind of look at this at the macroscopic level. So our first reaction, we're just going to take rubbing alcohol. That was the 3 blacks, 1 red, lots of whites, and dissolve it into some water. So add a little water. This is definitely not super exciting, but we're going to add our rubbing alcohol. You can kind of see, you might not be able to see on the camera, but it mixes just fine. Forms a solution. Definitely not like an oil and water situation there. It mixes very well together. Now we're going to do the same thing with salt. Add some water. Add a little bit of salt. Sodium chloride. Okay. And we're just going to stir until our solid dissolves. We'll talk about solubility here. Definitely increase the rate of solubility by heating this up. We don't have time to do that, though. It's going to go. So there you can see most of the particles are dissolved. I can see a few floating in the bottom, but pretty much they're dissolved. And so now what I want to show you is conductivity. Because the salt dissolves and forms ions that are loose in solution, this salt solution will actually conduct electricity. Okay. So what we're going to do right now is test conductivity. I'm going to look at the alcohol solution first. So we're going to place our conductivity device here. And as you can see, the light bulb is not being lit. That's because there are no ions in solution here, or not a sufficient enough ions, because water actually does ionize a little bit. But it's not sufficient enough to complete the circuit and get our light bulb to light. If we use our sodium chloride solution, which does have ions, we get a much different result. And you can see that it is allowing the circuit to be completed. It's allowing the light bulb to be lit. And so this solution conducts electricity because there are ions present. This solution with the rubbing alcohol does not conduct electricity because there are no ions present. This solution would be called a non-electrolyte. This solution would be called a strong